Hello everyone, my name is Debojit. I'm from the IITGN Robotics lab. So this talk is inspired from my parents. They always question me that, oh, I just saw a video about a robot doing like backflip. So why can't it do my kitchen tasks? So we all have seen these videos on LinkedIn, on YouTube. Our feed is just busted with all of these such videos where we can see robots doing backflips and a lot of agile motions. But here comes the real question. So if robots can do backflips, why can't they make a Vada pav? So let's analyze this question in more depth. So how can robots first handle deformable objects? Can you see the bun that you have? It's a deformable object. Second, how can robots handle multiple objects at the same point of time? I'm pretty sure from the morning when you grasp something, you also hold multiple objects at the same time. And then is the crucial question, how can robots coordinate and synchronize their motions using two arms, that is bimanual manipulation? And a very important question, can our robots match the skill of a local Vada pav seller, the speed at which it serves? So why are kitchen tasks, even the simpler ones, so difficult? So if you understand locomotion, you have a policy, you can train it for different terrains, but kitchen, it's different. You need to have grasping when you have occluded scenarios, you need bimanual manipulation, and a lot of other complexities which is not generalizable. So it's the right time to introduce ourselves. We are the IITGN Robotics lab. You saw a presentation yesterday which mostly covered the part of mobile robots and collaborative robotics. Next, in this section, you would see more about bimanual manipulation and grasping. We are based at IIT Gandhinagar campus, run by two professors, Professor Madhu and Professor Harish. So let's see how we are closing the Vada pav gap in humanoids. Let's first analyze for bimanual manipulation. So I am pretty sure that in the past 2 days, you have understood what is behavior cloning, reinforcement learning, and large-scale unsupervised learning. But I'll skip the introductions for these and directly move on to the challenges. So the main challenge with behavior cloning, as you have seen, is that you need a lot of data. And in reinforcement learning, as you will see that the bimanual tasks which I'm talking, how do you design rewards for them? And how do you make it generalized? And then large-scale unsupervised learning is something that you learn from internet videos, but they don't capture like force information and other crucial information about the physical world. So what's our approach? Classical control, we agree that classical control needs heavy hand tuning and hard-coded model, but it gives strong guarantees for stability, safety, and convergence. So learning models can infer a lot about the semantic information that is required for a control. So rich context about the surroundings. But they cannot give you formal guarantees for your actions and control. And they often don't incorporate physics into the system. So we here propose of a model where the action is something that is classical based and your learning kind of does the reasoning for those actions. So just to give you a brief idea, here we are talking not about VLA or action models. We're talking about classical approaches that is supported by some vision language model. So we do a range of bimanual tasks since morning, right? From taking a tray, handing over an object from one arm to the other, dumping an object into a garbage bin, and a couple of tasks. And I'm pretty sure you're not going to record 10,000 hours of this with imitation learning. And even if you think about reinforcement learning, you have to train a lot, you have to design a lot of rewards for them. So our idea is, can we have primitives to define actions in these? If you see on the red boxes out there, the tasks which are inside the red box, there we identified a very strong primitive is that we keep our hands always, the relative distance between the hand and the object constant, and also the orientation. Otherwise, we tend to damage the object. If you see the primitive, if you see the actions in the first blue box, you would realize that there's some kind of synchrony. What do I mean by synchrony? For example, for handover, you bring an object from one hand to the other in a very smooth, fluid, synchronous manner. And also for pouring tasks, you see that we kind of converge position first and then start pouring or change in orientation. And there are some bimanual tasks which are independent, which doesn't require any transfer of information between the two hands. So for the time being, let's name these as bimanual synchronous action, bimanual asynchronous action, and bimanual coordinated motion. These are some of the primitives that we have defined. We are working on defining some more primitives. So let's see this in action. Bimanual synchronous motion, primitive 1. So here you see two independent manipulators trying to hand over an object from one hand to the other in a synchronous manner. So it is a subtle information. You would observe that both the arm speed is synchronized to reach the handover pose at the same point of time. And I'll show you what happens if we don't. Now let's see the same action on a half humanoid platform. So now let us introduce obstacles along the path. And all of these computations that's happening is an online trajectory planning. So you can also introduce dynamic obstacles and also move obstacles around while the task is being executed and achieve synchrony. So many of you might think that, what if I just switch off the synchrony controller? So here the robot is more performing an independent action where there's no information sharing between both the arms. You kind of see the same motion, which was successful, this time fails to grasp the object. So that was primitive 1, that was synchronization. Now let's move to primitive 2, that is coordination, the constant relative distance between your arms while manipulating an object. So you see the relative distance between the arms don't change so that the object that is getting manipulated is not damaged. We're also currently exploring methods where we can use the whole body motion of a humanoid to do such manipulation tasks. This is about reorienting objects which are in hand. Since both the arms are sixed off, we couldn't achieve the full rotation of an object. These are some partial rotations around the axis. More about the math and research are in these research papers. You can take a snapshot, some of which are yet to get published, are under review. So we saw about these primitives: bimanual synchronous motion, bimanual asynchronous motion, and bimanual coordinated motion. Now the idea was that, can you have some spatiotemporal features that define these primitives more better? So for example, while uh, fitting a marker cap, you want to align the cross section first and then do the fitting action. For pouring, as I was telling you, that you need to converge the position and then start the orientation motion. Similar for a lot of coordination actions. We are also thinking of kind of integrating these into our primitives so that you have a family of primitives which a VLM or an LLM model could choose. And though these primitives gives you guarantees, you don't need to show so many of demonstrations. You have these embedded in your system, and the system actually chooses these primitives. No fine tuning, directly use the models which are available and be able to use these actions. So let's look at the second part of closing the Vada gap, grasping. So we saw a lot of demonstrations talking about how to use positional data, joint angles, joint velocities, end effector positions. But what we really need to start thinking is about force feedback and tactile feedback into the data. So this is one of the work carried out by another lab member who is currently who was an MTech student in the lab, about insights about how robots to pluck tomatoes. So here we are feeding also the tactile information into the network. In the interest of time, I'll skip introducing the network to you. Let's see the video in action. So here, original tomato is attached to the plate where the vine. The objective is to learn two actions. One is to detach it from the vine and also not to deform the object that it gets squished. So twist motion is to detach the tomato out of the vine, which is attached on the brown board. You can see that the tomato is detached and now is placed in the target. So that is most about grasping. One more last thing that we do we are exploring in grasping literature is about picking up multiple objects at the same point of time. These are some demonstrations with the leap hand in the lab. And here are the research papers that summarize most of the research mentioned in these two aspects of the work done in our lab. So let's get back to this Vada pav metaphor. So how can robots coordinate and synchronize their motions for doing bimanual manipulation? We are building a framework that can support a wide range of bimanual actions and is also not constrained by hard coding variables into the system. Second, how can robots handle deformable objects and dexterous skill learning is something that we are also exploring currently. And finally, about multi-object grasping. The kitchen still remains unconquered, but our robots are learning the ingredients: dexterity, coordination, contact, and control. Maybe we'll soon be able to make a vada pav with our robots, but still now we can't. And this last slide is really important. A lot of the work that we do in the lab is about manipulation and control. Because of the wider community about foundation pose, April tags, all of these things gets really easier for us to use. And second, ROS helps us to write hardware agnostic code. Some of the robots, we have it in our labs. Some of them is with our industrial partner in Noida, Adverb Technologies. So ROS helps us write that hardware agnostic code so that we can kind of test it across different hardwares. And I guess I'll keep the questions for the last. And last, you have the scan for opportunities tag. This scanner will lead you to three options. One for the IITGN Robotics Lab. Second, for the startup that was spoken about, Dexterity Robotics. And thirdly, about the AB6 robotics. Thank you.